Hiya! In this video I'm going to talk through the main numeracy skills that you'll be using in 3rd and 4th year physics. So I'm going to show you a couple of examples of significant figures, units of time and length, prefixes and scientific notation, and the graphs that we come across in physics. So significant figures, I actually have a separate YouTube video just about significant figures and how you would round to significant figures, so if you want more information then you can look there. But very briefly, if you have a question in physics and you want to be able to tell how many significant figures it has, your first rule is that you start counting at the first number that's not a zero. Again, I'll go into more information in my other video, but you start counting at the first number that's not a zero. So that number has 2 significant figures. Zeros are the ones that sometimes are and sometimes aren't. They're not significant if they are just showing place value. So think of that number as being the 2 and the 4 are the important ones, giving us information about the accuracy of the number. The zeros in front are just telling us the positioning of the 2 and the 4. The other example is something like 5,000. Those zeros are just there to show the fives in the thousands column. That number could have been rounded from 5,132 or something like that, and it's become roughly 5,000. So that has one significant figure. You need to be able to look at a question and look at the different numbers in a question and see how many significant figures they have, because that's your guide to how many significant figures you want your answer to have. The answer you get from your calculator will always be really accurate. There's no rounding happened so far. So the only thing you need to worry about is making sure you start counting at the first number that's not a zero. But for your final answer to the question, you want to make sure you've matched the number of significant figures in the question itself. So here's an example of a physics question. We're told the mass of a rocket and we want to know its weight. So if you've not come across this formula yet, don't worry, but you will learn about a formula. It says weight is mass times gravitational field strength. So if I stick in the value for mass, there's 0.94 kilograms. There's no value for g given, but that's actually in your data book. And g is 9.8. So the value that was given in the question, 0.94, start counting at the first number that's not a zero. That has 2 significant figures. The value that I took from the data sheet for the gravitational field strength, that also has 2 significant figures. So we want our answer to match that and have 2 significant figures. When I put that into my calculator, I get 9.21 newtons. But because I want to match the question, I'm going to write that as what it would be rounded, which is 9.2 newtons. You are allowed a bit of leeway here. You're allowed 1 less and 2 more significant figures than the question. As a general rule, what you should try to do is look at the numbers in the question, how many significant figures do they have, and match that with your final answer. Okay, next I want to look at units of time and length. So for our calculations in physics, we need to use the standard units. You should have a compendium if you're doing National 5 Physics, and in your compendium you'll see a table like this. And this is space for you to mark in the units as you go along. So this one is taken from the dynamics section. We've got the units of time, and then the units are seconds. So you would mark that in as you go, and the symbol is S for seconds. Speed, meters per second, and you'll learn all of these different ones as you go along. Distance, one you probably all know already, is meters. And an M. Now you might be thinking there are other units of time. We could have years, days, months, milliseconds, microseconds. Similarly for distance, you might have kilometers, micrometers, centimeters, light years. So we do have lots of different units that you may come across even in questions in physics, but when we're doing our calculations, we want to make sure we have our values in their standard units. So if we look at time, first of all, for our calculations we want time to be in seconds, and this is going to mean that we'll match up with other units if we want to calculate a speed. Speed's given in meters per second, so that matches up with our time in seconds. If we're talking about waves and frequency of waves, it's how many waves per second. So we need to make sure we have a consistent unit that we use for our calculations. So if we're going to need to change a time into seconds, we need to know that a minute is 60 seconds. There's 60 minutes in an hour, 24 hours in a day, and 365 days in a year. You will need to use that if you want to calculate the number of metres in a light year. So again, don't worry if you've not come across this yet. I just want to get into the numeracy of it just now. But a light year is the distance light travels in a year. So the formula that will help us work this out is distance is speed times time. So if we want to know how far light travels in a year, we can use the speed of light and that time of a year to work it out. So substituting in, distance is speed. The speed of light is 3 times 10 to the power 8 metres per second. But because it's per second, I need to know my time in seconds. Light travels 3 times 10 to the power 8 metres in a second. We want to scale that up to see how far would it go in a full year. So the value to multiply it by, I'm just going to do this in a different colour to make it stand out. The time that I need to get now, that needs to be in seconds. You can go off to the side and do this in a separate calculation if you find that easier. I'm just going to put it in the one just now. There's 1 year, but how many seconds in a year? Well, there are 60 seconds in a minute. So I'm going to start at the small scale, 60 seconds in a minute, then I need to get up to an hour. So I would multiply that value by 60 again to see how many seconds are in an hour. So 1 second times by 60, 60 seconds in a minute, times by 60, tell me how many seconds in an hour. Next interval will be a day. I take that value and times by 24. I'll have worked out how many seconds in a day, but we need to work out how many seconds in a year. I'm going to multiply that by 365. And if we do that, we get the value 9.46 times 10 to the power 15 metres. I know it's going to be in metres because speed was in metres per second. That's another reason why our units are so important here. I've gone for 3 significant figures with 9, 4 and 6. If you've said 9.5 times 10 to the 15 for instance, then that's totally fine. Okay, the other thing we need to be aware of with units, as I've mentioned briefly, is that we don't want the bit in front of it, the prefix that you sometimes hear, like microseconds or milliseconds. They're really useful for being able to get across the size big or small values, but we need to change the form of that before we get into the calculations. So we don't want the giga, milli, micro. I'll show you a table with all of them in a wee second. The exception is the unit of mass. Mass is the only one that we do want the prefix in front of it. The standard unit for mass is kilograms, not grams. So that's something to watch out for. Okay, so with the exception of mass, we want to get rid of that prefix before we use it in calculations. So if you have something measured in milli, if we look at this one here, so if you have a distance measured in millimetres, we will need to convert that into metres, or write it in metres, before we do any calculation. Same with kilometres, megametres, gigametres, and any of the prefixes you see there. A millimetre, you'll probably already be aware, there are 1,000 millimetres in a metre. So if we want to be able to write it in metres, that number would need to be divided by 1,000. So for instance, if you had 2 millimetres, we could take that value 2 and divide by 1,000 and say that that is 0.002 metres. There is a way of doing this that you might find a bit easier. You go straight to the calculator, which is to remember that milli is times 10 to the power minus 3. So this is a way of writing that in scientific notation. And your calculator can do this for you. Again, there's a separate video on how to use your scientific calculator where I go into this in a bit more detail. But if you spot the milli, then you can write this as 2 millimetres is 2 times 10 to the minus 3 metres. and those are the same value just written in a different way. This table shows the ones that you need to know for your National 5 physics. The highlighted one in the middle is a wee bit different to the other ones. If you notice centi. Centi is times 10 to the minus 2 because there are 100 centimetres in a metre. To get 1 centimetre written in metres, you would divide it by 100, 0.01 metres. The reason it's a bit different to the others is because if you look at the powers of the others, the powers go up in multiples of 3, times 10 to the 3, 6, 9, 12, minus 3, minus 6, minus 9, minus 12. But centi is so commonly used that it's still useful for us to know in physics. A couple of things to point out here is M as a symbol. M is used for mega and M is used for milli. It's really important that you read carefully whether it's a capital M or a small m. It's also important if you were to write that in an answer, make your handwriting really clear that it's capital M or a small m. Capital M is mega. There are a million volts in a megavolt, a million hertz in a megahertz, a million meters and megameters. So that's very different to milli, whereas with milli we have to go the other way. There would be 1,000 millivolts in just 1 volt. And the way that we write that kind of opposite direction is to say it's times 10 to the minus instead of times 10 to the positive. Okay, I'm just going to do an example calculation with this. An electromagnetic wave has a frequency of 1.2 GHz. So from this, we need to spot that the G stands for giga, and that's a prefix, which means it's in front of the unit, hertz. Hertz is the unit of frequency, tells you how many waves per second. So it's not 1.2 waves per second, it's 1.2 giga waves per second. If we go back to the page before and look at giga, come on pen, that's our giga line there. Recognise it because I had the symbol G, and giga means times 10 to the power 9. So that 1.2 is multiplied by 10 9 times, multiplying by 10 to the power of 9 before it tells us how many waves per second. The wavelength is fine for its units, it's just in meters, and that's the standard unit of length, and wavelength is just a length, so that's absolutely fine. The formula that help us here, again don't worry if you've not come across it, is V equals F lambda. The question is a show that question, so we don't actually know the 0.25 meters to put in, but we do know the other two. V isn't mentioned anywhere, but something you will learn if you've not already learned already is that all electromagnetic waves travel at the speed of light. Frequency is the thing we're trying to, frequency is the thing we know, that was 1.2, but we need to make sure we include that giga times 10 to the power 9. And then lambda is the thing we're trying to work out. To get lambda on its own, if we look at what the lambda was doing on the right hand side, the lambda was being multiplied by 1.2 times 10 to the power 9. So to get the lambda on its own, that 1.2 times 10 to the 9 needs to become a divide on the other side. So if I write that out, we have 3 times 10 to the power 8, and then separating that times 1.2 to times 10 to the power 9 from the lambda makes it divide by 1.2 times 10 to the power 9. If you need help putting that into your scientific calculator, that's covered in my other video on how to use your scientific calculator. Okay, and if we put this into calculator, we get 0.25 meters. Because this was a show that question, it did actually tell us the answer at the beginning. Show that the wavelength is 0.25 meters, so we can check that we got it right. Okay, the next thing I want to talk about is graphs. You'll see these videos on this YouTube channel for different subjects, and the way that the graphs are used in different subjects does vary. In physics, we're looking for overall trends and overall relationships, so we use something called a line of best fit. If you look at this graph here, it's showing the relationship between acceleration and force. This is an experiment that you do quite early on in third year when you learn about Newton's second law. So you're going to apply a force and measure the acceleration. These results are quite consistent. You can see those points lie on an almost perfect straight line, but you are going to get values that don't fit in perfectly. Okay, there are a few different reasons for this. There could be an error with your reading, there could be something not weighed perfectly, there could be air resistance, there could be different things that are causing our results not to be absolutely perfect. But what we can see from the results is that we can see the trend that they would be in. We can see the overall trend of this graph. So although this point up here doesn't lie perfectly on the line, that's fine because our point of the graph is to show that overall relationship. We want to be able to see that as the accelerating force increases, the acceleration increases. The other thing we can do from drawing a line of best fit that we wouldn't be able to do with a dot to dot is continue the graph to predict what would happen if we had larger forces. So this straight line could be continued on. Oops, it's in white, that's not very helpful. Sorry. There we go. Could be continued on to say what if we added a force of 10 newtons, or if I had more space, continue on what about 12 newtons, 14 newtons, and we can predict what acceleration would occur with those forces because we know to expect that to continue to go in a straight line. If we'd drawn a dot to dot, then that wouldn't be able to get extended in the same way. There are other useful things we can do with the straight line, such as calculate its gradient, and that will tell you different things depending on the topic that you're talking about. In this example, you can see that extending use of the straight line a wee bit more clearly. So if you notice up here, we've got the crosses showing all the values, and they don't lie in a perfect straight line, but there is still a very clear correlation, a very clear trend. So we draw a line of best fit that shows the gradient, that shows that general trend. Okay, it's going through a couple off in the middle, and it's got a roughly equal split between the points above and the points below. But by drawing a straight line, we can analyse it, we can calculate the gradient, things like that, but we can also extend it to predict what would happen at other values. And for some topics this is really important. For this graph here, it's showing the relationship between temperature and pressure. When you do this experiment in class, we're limited to what temperatures we can work with. But if we can choose to extend our scale, we can extend our graph to predict, well, what would happen at very, very cold temperatures that we wouldn't possibly be able to work with in a lab. And we can actually go on to predict the coldest possible temperature by extending it all the way back to reach that temperature x-axis there. Okay, so lines of best fit are what we use in physics. They're useful because we can use them to describe the overall trend, and that's what we're looking for. We're not looking at those individual scenarios. We want to see what's the overall relationship, what do we think would happen if we kept going on to higher temperatures or went back onto lower temperatures. And we can also use them to predict individual temperatures. So we would expect another value to lie on that straight line. We can use that to make predictions about what temperatures would go with what pressures. The final point I'd like to make is down the bottom there. It says never break the scale. So this is something we come across sometimes. I know you see it in other subjects. That's where you see a wee zigzag on the axis, and that lets you like fast forward some of the numbers. When you do this experiment in class, you'll maybe notice that all your pressure values are quite close together, between 100 and 130 in this graph. So when you're drawing out this graph, you might feel like that's a bit of wasted space, having to go 10, 20, 30, 40, 50, all the way up to 100 to have all your values really close together there. So what some people want to do, because they've seen it in other subjects or other places, is use that fast forward. It's really important that you never use that in physics. As I just said, one of the main benefits of our straight line is being able to continue it to see what would happen at higher temperatures and at lower temperatures. If you have that fast forward, then you wouldn't be able to do that. Okay, because if you imagine if the fast forward was on this graph here, then that whole line would have been dragged further down, and that would totally affect what values we're going to be going through. Okay, so make sure never break the scale, never do that fast forward in physics. Okay, final point on graphs. Our graphs are, as I said, are to show relationships. Relationships they need to know about are direct proportion and inverse proportion, and they're both shown in this graph here. When you learn about the relationship between pressure and volume, and if you were to draw the graph of your results when you do this experiment, you get that curved shape that you see on the left hand graph there. So that is showing inverse proportion between pressure and volume. Okay, an increase in one is causing the same percentage increase in the other. If they're inversely proportional though, what we can do is change volume into 1 over volume, or the inverse of volume, and this gives us pressure being directly proportional to 1 over volume. Okay, you'll go into this in a lot more detail in class, so don't worry too much about it just now. The main point I want you to get across to you just now is that how you can tell from looking at a graph whether it's an inverse proportion or direct proportion. So I just want you to recognise these shapes. On the left hand side we've got inverse proportion, and here is what our graph of direct proportion looks like. Okay, we want to be really clear if we're saying something's in direct proportion though, and a straight line is nice and easy for us to analyse. Okay, as I said, we can work out the gradient of it, and we can tell by looking at it that it's a perfect straight line. Final point down the bottom, something to make sure you're aware of though. A graph showing direct proportion is a straight line going through the origin. It's really important that it goes through the origin. Direct proportion is when the ratio of the two quantities stays constant. Okay, or another way of describing it is to say that a percentage increase in one causes the same percentage increase in the other. It needs to go through the origin to do this. If you know from your maths as well, the general equation of a straight line going through the origin is y equals mx. This is saying the value you get in your y-axis is always going to be that same constant times the number in your x-axis. For that to be true, you will always go through the value 0, 0. Okay, if you're just at the beginning of third year, you maybe not got into that just yet with maths, but you will come across it, and if all you get from the video just now is just that with direct proportion, make sure you're only stating that claim if it goes through the origin. Okay, hopefully you found that video useful. A couple of things just to remind you of, a couple of resources that might help you in future, is we have a physics compendium, which is what I show in this slide here actually. This is from your compendium, and this is from your compendium as well. So you've got your compendium that will help you keep a record of the units that you're using in physics, and also keep you right with your prefixes. There's also a numeracy reference book that talks over the main numeracy skills that I've talked about in this video, and I've got my YouTube videos for more specific videos. So there's the one on rounding to significant figures and how to use your scientific calculator, which tie in well with what I've talked about in this video. Okay, thanks for watching, hopefully you found it helpful.